So in today's lecture we are going to see about the time domain specifications of control systems. Okay. So the desired performance characteristics of any control systems that are specified in terms of time domain specifications. For example, systems, just you consider a system with some storage elements, just like a inductor or capacitors. So they cannot respond instantaneously. So and they will exhibit some transient responses. Transient response means the response of the system, it will not come to a steady state immediately, but it will take some time to reach to the steady state response. So because of these disturbances or the disturbances plus or the energy which are already stored in the energy storage elements, they produces some response, they are called transient responses. So the desired performance characteristics of a system of any order, so that may be specified in terms of your transient response to unit step input signal. So we will be considering the unit step as the input signal to find the performance characteristics of such a system. Just to see an example, so here you are having the input signal, it is unit step signal, its amplitude is 1. So this produces a time response like this. So this is your output C of t. So here for different values of damping factor, you will get a different responses. So we have already seen the different classes of or different cases of systems depending upon the value of this damping factor. Suppose if the damping factor or if the particular system is of high damping factor, for example theta is equal to 2, then it will take more time to reach its steady state response. For example, if the maximum response or the steady state response of this particular system is equal to 1, then it will not reach this 1 in short duration. It will take more time to reach the steady state response. For example, if the theta, the value of theta is equal to 2. So if you reduce the value of theta, if theta is equal to 1, it will take a little bit lesser time to reach its steady state value. So this is the response when the value of theta is equal to 1. And suppose if you reduce the value of theta further, for example in the underdamped case, then the response will be like this. So already we have seen this response in the case of second order system. So here in this case the value of theta may be it is less than 1, or it may be some theta equal to some 0.4 or something, right? So in this way, if you reduce the value of this damping factor, it will quickly reach us to its steady state value. So in the case of zeta equal to 1 or critically damped system, suddenly it will be reaching its steady state value. So within a short duration itself it will reach its steady state value. So the response what we obtain before reaching its steady state value, generally we will be calling it as transient response. And this transient response, of course it depends upon the system's initial conditions. There may be some storage elements. So these storage elements may cause the system or these storage elements, the energy stored in these storage elements will produce a response. That response is called transient response. Therefore, to compare the time response of various systems, so it is necessary to start with the standard initial conditions. So the most practical standard, that is to start with the system at rest. So the output and all time derivatives before t equal to 0 will be equal to 0, right? So the transient response of a particular any control system that do exhibits damped oscillation before reaching its steady state. Understood? So the transient response plays a major role that characterizes a system. So the transient response characteristics of a control system to unit step input, it is specified using various terms. So that terms only we are going to see in this lecture. So what are the terms? Let us see. The first one is the delay time. So this delay time is represented as T suffix D. So this represents the delay time. So we will see elaborately these topics one by one. The next one is the rise time. So this rise time is represented as TR. And the third one is the peak time. So it is represented as T suffix P, TP. And the fourth one is the maximum overshoot. Maximum overshoot. So it is represented as M suffix P, capital M suffix P, MP. And final one is the settling time. The settling time is represented as T suffix S. So these are the 5 important time domain specifications. So once again I am repeating. The first one is the delay time, it is represented as TD. The next one is the rise time, it is represented as TR. The next one is the peak time, it is represented as TP. The maximum overshoot, MP. And finally the settling time, TS. So let us see these parameters, these time domain specifications one by one. The first time domain specification is the delay time. So it is represented as T suffix D. Delay time is represented as T D suffix D. So it is the time taken for response to reach 50% of the final value. Understood? So suppose let us see the response from a system. So this is your C of t. So you are getting a damped response like this. So this one is the steady state value, right? So this is its maximum response, right? So this is the maximum response, or it is represented as 1. So 50% of its response means this point should be 0.5. Understood? So the time taken to reach the response to reach 50% of its maximum value. So this is your 50%, right? So this time interval is called your delay time. This is TD, or delay time. So delay time is nothing but the time taken for response to reach 50% of the final value for the very first time, right? So that is the meaning. So here this response to reach its 50% of its final value, this one takes this much of time. You can see this in this diagram. So it is represented as T suffix D, or the delay time. The next one is the rise time. So it is represented as TR. So actually it is the time taken for response to rise from 0 to 100% for the very first time. So that is known as rise time. See here. So here the response starts at time t equal to 0, and so it reaches its 50% of its maximum value. So that time is represented as delay time, and once again the response is keep on increasing, and it reaches, for the very first time it reaches its maximum value. Its maximum value is 1. So this time is called your rise time. So this is called your rise time. So this point is your TR, and this time is called your rise time, TR. Understood? So the rise time is nothing but the time taken for response to rise from 0 to 100% for the very first time. So for underdamped system, the rise time is calculated from 0 to 100%. But for overdamped system, it is the time taken by the response to rise from 10% to 90%. So for a overdamped case, for underdamped case, you will be calculating the rise time starting from 0 to reach its 100% for the very first time. For overdamped system, you will be calculating this rise time for the response to rise from 10%, rise from 10%. So this point may be your 10% to 90%. So this duration is called your rise time, TR, in the case of overdamped system. So 10% to 90%. For underdamped system, it is 0 to 100%. The next time domain specification is your peak time. What is peak time? So peak time is the time taken for the response to reach the peak value the very first time, or we can say it is the time taken for the response to reach the peak overshoot MP. Understood? So what is the peak value? See this response. So this is nothing but the peak value. So in this diagram, this point represents the peak value of the response. So the time taken for the response to reach its peak value or the maximum value is called its peak time. So this time is now called TP or peak time. Understood? So this is your maximum point, or this point will be representing this point as C of TP. The response at which it reaches, or the response reaches its maximum time. So this is known as peak time. The next time domain specification is the peak overshoot. So let us see what is peak overshoot. So actually it is defined as the ratio of the maximum peak value to the final value, where the maximum peak value is measured from final value. Understood? So it is nothing but the ratio of the maximum peak value to the final value. Understood? So let us consider. So let us take the C of infinity as your final value of C of t. Final value of your response C of t, and your C of TP, it represents the maximum value of C of t. This is known as maximum value of C of t, right? So one is the C of infinity, it is nothing but the final value of C of t. The another one is C of TP, it is nothing but the maximum value of C of t. Therefore we can define this peak overshoot as MP is equal to C of TP minus C of infinity divided by C of infinity. So this is the definition of your peak overshoot. So usually this peak overshoot is calculated in terms of percentage value, right? So therefore the percentage MP or percentage peak value or percentage peak overshoot is equal to C of TP minus C of infinity divided by C of infinity into 100. This is what our percentage MP or percentage peak overshoot. And the final time domain specification is your settling time. Settling time. So what do you mean by settling time? TS. So it is defined as the time taken by the response to reach and stay within a specified error range, right? So within a specified error range. So you are specifying some error range. The settling time is the time taken by the response to reach and stay within a specified error range. For example, just to see this diagram. So here suppose you have specified the specified error as 2%, 2% as your specified error, and therefore the time taken for the response to reach its 2% of specified error. So this time, the time starting from this point to this point, this is known as your settling time, TS, right? So exactly the response will not reach, or it will be reaching its steady state value of this 1. Instead it will be oscillating, small oscillations will be there, and that oscillation error you will be specifying it, so that is known as percentage of error, right? So within this specified percentage of error, if your response comes or if your response reach, then the time taken starting from 0 to your specified error range, it is called the settling time. Understood? So these are the important time domain specifications. Next, you are having small derivations to calculate these time domain specifications, right? First one, let us see these derivations. Derivation for first one is the rise time. Okay, so what is rise time? See, so already you know the definition of rise time. It is the time taken for response to rise from 0 to 100% for the very first time. 0 to 100% for the very first time, right? So let us consider the response of a second order system, the underdamped response of or a system in the case of underdamped, right? So already we have derived this response in the last class. So the response of an underdamped system, C of t is equal to 1 minus e power minus zeta omega n into tr divided by square root of 1 minus zeta square into sine omega dt plus theta. This is what the response of an underdamped system for unit step signal as input. Understood? So at time t equal to tr, at the time t equal to tr, tr means its rise time, the response we can represent the response as c of tr, isn't it? C of tr. So when it reaches its maximum value, you can see in this diagram, right? So this is your 100% response, right? So the value at this point, the value of the response at this point is equal to 1. Therefore we can write c of tr is equal to 1. At time t equal to tr, the value of c of tr is equal to 1. Understood? Therefore we can write c of tr is equal to 1 minus this one, e power minus zeta omega n into tr divided by square root of 1 minus zeta square into sine omega d t. Instead of t you put a tr. Okay, so sine omega d tr plus theta is equal to 1. So you just equate this value to 1 and you replace all t's with a tr. Understood? And from this you need to calculate the value of this tr, right? So we can write this as, so we can cancel out this 1 and right, this 1 and this 1. Therefore the remaining thing is, we can write this as, so let us see. Therefore we can write this as minus e power minus zeta omega n into tr divided by square root of 1 minus zeta square into sine omega d tr plus theta is equal to 0, we can write. Understood? So now in this case, here this value of this e power minus zeta omega tr, it is not equal to 0. So you are equating the entire equation to 0, and therefore e power minus zeta omega n tr, this is not equal to 0. Therefore, this term can be equal to 0. Therefore, we can write this as sine. Therefore, we can write sine omega d tr plus theta can be equal to 0. Understood? So, the value of sine phi equal to 0. Already you know sine phi equal to 0. The value of phi is equal to 0. It can be 0, pi or 2 pi or 3 pi, etc. Right? For all these value of 5, the sine phi equal to 0. Therefore, we can write this as omega d tr plus theta is equal to pi, we can write. Or we can write this as omega d tr is equal to pi minus theta. Or we need just tr. Therefore, your rise time tr is equal to pi minus theta divided by omega d. Already you know what is the formula for this omega d, right? So, omega d is equal to omega n into square root of 1 minus theta square. Understood? So, already we have constructed a right angle triangle with theta and 1 minus theta, square root of 1 minus theta square as two sides. So, this one is theta and this is square root of 1 minus theta square, and this angle is theta, means this will be equal to 1. Therefore, here in this case sin theta is equal to your opposite side by hypotenuse, square root of 1 minus theta square, and cos theta is equal to theta, and tan theta is equal to opposite side by adjacent side, which is equal to square root of 1 minus theta square divided by theta, or we can write theta is equal to tan inverse of square root of 1 minus theta square divided by theta, we can write. Now, if you substitute this value here in this equation, you will get the final value of this tr. Therefore, we can write this tr is equal to, therefore, we can write this tr is equal to pi minus theta. Theta is nothing but your tan inverse square root of 1 minus theta square divided by theta, the whole divided by omega d. Omega d is your omega n into square root of 1 minus theta square. So, this value is in seconds. This is time, right? This is what the derivation for the your tr or rise time. The next derivation is for peak time. Okay, the next one is for peak time. So, peak time will be representing this peak time as Tp. Understood? So, to find the expression for the peak time, just we need to differentiate. Your response C of t, and if you differentiate it, and if you equate this to we can write this as d by dt of C of t is equal to 0, you will get the value of this peak time. Understood? Therefore, we can write this as d by dt of C of t, right, at t equal to your peak time, Tp is equal to 0, right. So, here also you need to, we are considering the response of your underdamped second order system. So, you know what is C of t. C of t is equal to 1 minus e power minus theta omega n into t divided by square root of 1 minus zeta square into sin omega d into t plus theta. Understood? So, now you need to differentiate this equation with respect to t. So, I am differentiating this, right. Therefore, we will be getting d by dt of C of t, d by dt of C of t is equal to, for this one there is no the differentiation is 0, right. So, we can write it as minus e power minus theta omega n into t divided by square root of 1 minus theta square, the first term, right. So, what is the differentiation of e power theta? E power at, once again e power at into a, right. So, here the constant is minus theta omega n okay, into the second term sin omega dt plus theta. Okay, so the differentiation of the first term into the second term plus the first term into minus e power minus theta omega n into t divided by square root of 1 minus zeta square into the differentiation of the second term. The differentiation of sin theta is cos theta. So cos omega d t plus theta into this value omega d. Understood? This is what the differentiation. Now omega d, the value of omega d is nothing but omega n into square root of theta square. The value of omega d is equal to omega n into square root of 1 minus theta square, right? Therefore we can write this d by dt of c of t as d by dt of c of t equal to e power minus theta omega n into t divided by square root of 1 minus theta square into theta omega n into sin omega d t plus theta, the second term minus omega n into square root of 1 minus zeta square by 1 minus square root of 1 minus zeta square into e power minus theta omega n into t into cos omega dt plus theta. This is what the answer, right? Now we can simplify this as, which is equal to omega n into e power minus theta omega n into t divided by square root of 1 minus theta square into, so you are taking these factors common because these two things are common, the into theta into sin omega dt plus theta minus square root of 1 minus theta square into cos omega dt plus theta. Understood? So from this right angled triangle we can write theta is equal to just cos theta, isn't it? Theta equal to cos theta and square root of 1 minus theta square equal to sin theta. So we can simplify this as omega n divided by square root of 1 minus zeta square into e power minus zeta omega n into t into, so instead of zeta you put cos theta into sin omega dt plus theta, right, minus sin theta into, because square root of 1 minus theta square is sin theta, so sin theta into cos omega dt plus theta. This is what the answer, right? So in the next step we can simplify this further, right? So we can rearrange this as omega n divided by square root of 1 minus zeta square into e power minus zeta omega n into t into, we can rearrange this, sin omega dt plus theta into cos theta minus cos omega dt plus theta into sin theta. So this is nothing but sin a cos b minus cos a sin b, right? Now we can write this as sin a minus b. Therefore we can write this as, which is equal to omega n divided by square root of 1 minus zeta square into e power minus zeta omega n into t into sin omega dt plus theta minus theta. Okay, so this is the simplified form. Further we can simplify this as, just to see this, so we can write this as, which is equal to omega n divided by square root of 1 minus zeta square into e power minus zeta omega n into t into sin omega dt. So plus theta and minus theta we can cancel. So it is nothing but sin omega dt, sin omega d into t. So at t equal to Tp, peak time, when the time reaches its peak time, right, this d by dt of c of t will be equal to the differential component of this response will be equal to 0. Therefore we can write this one as omega n divided by square root of 1 minus zeta square into e power minus zeta omega n into, instead of t you put Tp, into sine omega d Tp is equal to 0. Sin omega d Tp is equal to 0. Therefore, this term, this exponential term is not equal to 0, or we can write e power minus zeta omega n Tp. This is not equal to 0. Therefore, only this term, that is sin omega d Tp, can be equal to 0 for the value of phi equal to 0, pi, 2 pi, etc. Right? Therefore, we can write this as omega d Tp is equal to pi, or we can write Tp is equal to pi divided by omega d. Understood? This is what the final equation. So instead of omega d, you can substitute the value. So or we can write this as Tp is equal to